Hi, my name is Chris. I work as a production engineer at Facebook London, just up the road in Euston. I'm going to be giving a kind of whistle-stop tour of the new version of control groups added in Linux 4.5. Don't worry if you have not the faintest idea what I'm talking about when I say the word cgroups. We're going to go kind of over how cgroups worked in the past, how we're planning to make them work in the future, and some of the contrasts between that. So in this talk, I'm going to be going over the new version of cgroups. I'll give you like this short introduction, what they're used for, where you may have seen them before. If you've been interacting with something called cgroups in the past, it's almost certainly true that you've been interacting with version 1. And V1 has been out since 2008, and it's been one of the main things which has assisted us in having this great level of containerization that we have now, and the reason why we're all here. And obviously, it has a whole bunch of good stuff since we're talking about it and we're using it in containers every single day. But it also has a bunch of usability foibles, general pitfalls, things which are very easy to mess up, and things which are actually impossible to do. So cgroupv2 is an attempt to fix these. And cgroupv2 is very much under active development right now. cgroupv1 and cgroupv2 share the same core technology, but the API exposed to user spaces is different. And that allows us to do different things based on the fact that you use cgroupv2. So since I'm talking about cgroupv2, not cgroupv1.1, I want to go over like why we chose to do an API break. I want to go over why an API break was chosen over doing incremental changes. I want to go over some of the fundamental design decisions in V2 as well, and why they were made in that way. Also, a lot of V2 was made in order to allow future changes to happen. So some of the stuff was still being worked on. Some of the changes are things that we want to do in future and things that are being enabled. So I want to go over what core parts are ready and which bits we're still working on and what's ready for use in production right now. So first, a little bit about me. I've been working at Facebook for about 3 years. I'm working in this team called Web Foundation. Technically, as you'd expect from the name, we're responsible for the web servers at Facebook, but web servers are generally pretty simple. Like they serve you some pictures, they serve you some cat pictures, whatever, and they go about their merry way. They're stateless and they're not particularly interesting in most cases, with some exceptions. So we also ended up becoming kind of the overall guardians of site reliability at Facebook. So we are the people that lead incident resolution, incident management, whether inside the web stack or out. We deal with all sorts of incidents on a daily basis. And yeah, we're the team which leads kind of incident resolution across Facebook in general. And we have a whole bunch of different people inside our team, and this kind of explains why we're so interested in cgroups. We have system debuggers, which is basically the kind of stuff I do. I spend a lot of my time working out why systems act the way they do and trying to fix them. We also have domain experts in stuff like our cache and RPC and task scheduler called Tupperware, which is a bit like Kubernetes. And we also have experts in stuff like push and hack and HHVM, which is our JIT compiler for PHP. And when not working on cgroups, I work mostly, like I said, on making systems work. So that kind of explains why I got involved rolling out cgroups inside Facebook. We have many, many hundreds of thousands of servers, and we run a bunch of services on those servers, usually not only one on a single server. And I care a lot about limiting the failure domains that are on those servers. Most real outages at Facebook tend to be caused not because one system failed, but because of a cascading failure between different systems. And I think that's true for a lot of mature companies. And we want to be able to restrict those. We want to be able to stop service failures from affecting one another and beginning to screw up the whole system. And there are a lot of things that you need to do to be able to get to that state, right? You need to be able to understand and isolate your dependencies for your services in general. This is also a huge part. But another bit is we don't just want one service taking all of the resources, say all of the memory or all of the CPU on the system, because that really is also equally as bad on a day-to-day basis. So let's look at kind of like a typical server from a cgroup perspective. So we have kind of the core workload. Say this is like the main thing you want to do on the machine. If you were describing this server to somebody, you would describe it as doing this. This might not be a physical server, of course. This might be something inside a container or whatever. But ultimately, it's the main thing you want to do on your machine. For example, HHVM on our web servers, or Proxygen, which is our HTTPS load balancer. And yeah, this is generally the thing you think about when you talk about that machine. But then you also have this core group of system services. Most companies of any size that have existed for a significant number of years have some kind of services which they've ended up building, which are specific to their infrastructure. It might be something you built, might be something which you've inherited from the open source community. But in general, you end up with stuff which does like metric collection, for example, say Grafana or whatever, or StatsD. But ultimately, I don't want these pieces of software, say metric collection daemons, to start interfering with the core workload. There is another talk as well given by a friend of mine called Rachel Kroll, who also works at Facebook, which goes over some of the incidents we've had at Facebook, and one was a metric collection daemon, which began to take like gigabytes and gigabytes and gigabytes of RAM until it oomed the machine, which was obviously not what we wanted. So we want to be able to prevent those kind of things from happening. Chef is also, for example, vital for an up-to-date machine and a correctly configured machine, but we don't want it to start taking 100% CPU. For whatever reason, we have a bug in our cookbooks, or they have a bug in Chef. We don't want it to start to interfere with the web request. That's the ultimate point here. Then you kind of have these rarer things like ad hoc queries and debugging. Typically, you only know that you need these when you're retroactively dealing with a situation. Like these can vary in importance. Say you want to run a TCP dump because you don't understand what's going on right now, and it's messing up the whole of production. You want to generally let people dynamically determine the importance of these things. So this kind of problem is a really common use case for cgroups. So in the previous slide, we've been talking about kind of multiple processes which fit inside all of these kind of archetypes. So a control group is very flexible. It can consist of as many or as few processes as you like, and you can set limits and all sorts of other things on that cgroup. For example, you can have all services in a cgroup, which is for your non-core services, or you can have a cgroup for your non-core services and have children of that cgroup which contain your non-core services. You can have it basically any way you like. The idea here is the framework should be flexible to your needs and requirements and not impose a structure on you. We should allow you to design in the way that best befits your organization. So a cgroup is a control group. They're one and the same. And as you might have guessed by now, basically what they do most of the time, but not all of the time, is resource management on Linux, where resource means something you share, CPU, I/O, memory, whatever. And management can mean a whole bunch of stuff, like limiting, say, when you hit a particular threshold, we want to take some action. Thresholds where, say, you hit a threshold and when you want to take some other action, we branch into a different code path and do some kind of other actions based on that, and I'll go into that in a bit. And yeah, generally the idea here is that they manage resources and allow your processes to operate independently of each other. So cgroups are controlled by directories at /sysfs cgroup. There's no system call interface, at least we don't currently have one. So creation, deletion, and modification of cgroups all happen by your standard system calls, make dir, rmdir, write. The nice thing about having a directory for this is, of course, you can basically access the cgroup interface in any language. You don't have to go around futzing around with some C library or write some program in C++ or whatever to get access to the system call interface. You just do things with files and sysfs cgroup, and that should be basically not that difficult. Usually, you do want the writing of the hierarchy to be done by one application, which we use systemd, for example. But ultimately, you can do it with other applications, and the more common case is to read things from that hierarchy. Each resource interface is provided by a controller. So a controller is essentially something which provides the files you can manipulate inside this directory structure to, say, set a memory limit, and then provides those values to the kernel, and the kernel decides what to do differently based on the values which you provided. So manipulating these values tells the kernel to do something different. So as mentioned previously, like workload isolation is a super huge use case for cgroups. You might have many background jobs on a machine which you don't want to affect the main workload. And the same is kind of true for asynchronous jobs. So some jobs, for example, Facebook has a tier which runs asynchronous jobs, and some jobs may have a higher priority than others. What priority means is very contextual. Priority might be something to do with resources usually. Typically, it has something to do with how much CPU we give, how much memory we give, how much time we give. These are kind of typically the kind of things which are possible to do with cgroups. We also have kind of shared environments which are kind of similar, like say you're a VPS provider and you want to provide all your customers with a consistent experience. You want to be able to provide people with as many resources as you can give them at the particular time, but as soon as somebody else comes and demands those resources, give them back to them. So you kind of give them the full machine on a best effort basis. And that's another use case for cgroups. So you might think that, hey, my favorite product X has like the same functionality. So why is this guy talking about cgroups when product X has way better functionality? Well, that's probably not true, because if your application has been built in the last 8 years, the cgroup API has been the most mature API to do this for a very, very long time. And it's almost certainly true that this is at the core of the resource management that your application does. So this affects you whether you know what cgroups are or not. If you're in this room, it's almost certain that you use cgroups whether you know it or not. So let's look at how this works in cgroup concretely. So like I mentioned, if you've had some interaction with cgroup in like the last 8 years, which is as long as this existed, you've almost certainly been using version 1. So version 2 has been in development for about 5 years now, but we only made it stable quite recently in kernel 4.5. Even on recent kernels, you'll only typically see version 1 at sysfs cgroup. The reason for that is the kernel actually supports booting, actually boots supporting both. But since the version 2 hierarchy is backwards incompatible, your applications have to support it. So we're not at a stage where we're comfortable doing that kind of stuff up front for the moment. So I'll also go into how to use the v2 hierarchy at the end. So this also is kind of like a cell talk on why you should care about cgroup v2, why it might be useful for you as a consumer, whether you're making the containerization software or using it. Generally, it's something you should be invested in and care about. So in v1, sysfs cgroup contains controller names as directories at the top level. So you have resources like CPU, memory, PIDs, things which you want to be able to limit or account for. So inside these directories are hierarchies for each resource. You can see kind of a directory hierarchy at the bottom inside the PIDs hierarchy. The PIDs hierarchy changes how many tasks or PIDs you can have, TIDs in v1, that you can have in a cgroup. And you get files which you manipulate, like, oh, I set this file, it sets the maximum number of PIDs in this cgroup, and so forth. Yeah, and the same is true for, say, memory or CPU. You have files related to that, and you set them inside the cgroup. So each resource has its own hierarchy for resource distribution. So resource A here could be, say, memory. Resource B could be CPU. And even if cgroup 3 had the same name as cgroup 1, say they're both called foo, which is a common enough case, say when it gets set up with systemd, the kernel sees them as completely unrelated. And this has a whole bunch of really kind of bad implications, which I'll go into later. Cgroups are also being nested inside each other in this example. For example, cgroup 2 is a child of cgroup 1. Typically, what this means is that cgroup 2 here will inherit the properties of cgroup 1, and you can set more restrictive limits in the child. So you set a limit in cgroup 1, you can also set a proportion of that limit in cgroup 2, or the maximum. So the resource that controls this cgroup changes what it does. The main point here is cgroups only exist in the unique context of their own resource. For example, if resource B is memory here, you only have files related to memory in the resource B hierarchy. One file, memory.limited bytes, sets, as you would expect, the memory limited bytes. And other files in the cgroup directory perform like a bunch of different operations related to memory as well. The main thing is you can only change things related to that resource in a single hierarchy. One PID isn't exactly one cgroup per resource as well. So PID2 here is explicitly assigned to cgroups for resources A and C, but we didn't explicitly assign it in resource B, so it goes to what's called the root cgroup. So the root cgroup is at the base of the directory for the controller. So say if resource B here is memory, then it will be sysfs cgroup memory, and then you see PIDs inside there. The root cgroup is essentially limitless. It's the base at which you distribute resources across your system. So you can't really set any limits there, which is kind of a problem if stuff is in there. You still get some accounting, but that's about it. You don't really get any control over what's there. So this is concretely how it looks. So just so that we're clear on everything before we move to v2, because it's very important to have the context. So you start with sysfs cgroup, which is where it's typically mounted, but it doesn't have to be. And inside you have the resources. Inside there you have a cgroup hierarchy per resource. And once again, if you have the same name, say ad hoc and BG here in multiple resources, they still have absolutely no relation to each other from the kernel's perspective, and this has a whole bunch of negative effects. So in cgroup version 2, we actually see something quite different at sysfs cgroup. We don't see the resources at all at sysfs cgroup. We used to see CPU, memory, PIDs, that kind of stuff. Now we see the cgroup directories themselves. .slice is just a systemd terminology. It has no meaning to cgroups, but yeah, we see the cgroups themselves, not resources. So how do those particular cgroups know which resources they should apply to? So essentially, the way that this works is inverted. Now, instead of having cgroups created in the context of a particular resource, resources are enabled or disabled in the context of a particular cgroup subtree. That is, you enable or disable, say, a CPU controller in cgroup 1 or cgroup 2, and you manage that resource only in the context of that cgroup. This allows us to be way more flexible and have one single cgroup hierarchy to rule them all. This means like there's a special file, which I'll go into in a moment, where you echo, say, plus CPU, and it gives you files related to CPU for your cgroup. So in cgroup version 2, you can see the hierarchy is kind of similar, but note the differences. So instead of having 4 cgroups under the top level, we now have 2. Let's look at this again. Where we have 4, now we have 2. So also, this means like instead of having a cgroup per resource, we now have resources per cgroup. This allows us to opt in at will to resources that we care about. So as you can see here, we have kind of the opposite. We have a cgroup hierarchy per resource. That is, cgroups only exist in the unique context of their own resource. And remember, again, because it's very important, that in version 1, cgroups with the same name and in different resources have no relation to each other. So the way that you enable these controllers in a particular cgroup is you write to this file, cgroup.substreecontrol, and you write, say, plus memory or plus PIDs, and then that cgroup's children have that controller enabled for them. If you say have cgroup.substreecontrol with memory and then you disable it in the child, that child then competes freely for memory. But you must, in real life, have the memory PIDs and I/O controllers enabled at the top level as well, because otherwise they can't inherit it. They have to inherit it from their parent, and their parent has to inherit it from their parent, and so on. So kind of the fundamental differences here are like that resources apply to cgroups now. This is really, really, really important for really common operations in Linux. Like page cache writebacks are probably the most common operation which require this. It's previously really, really, really difficult to decide what we should do when we're performing a domain, multi-domain action, i.e. one which spans multiple kinds of resources, page cache writebacks being a really common one. And the reason that doesn't work very well in version 1 is because we have separate cgroup hierarchies per resource, so we can't infer the relation of 2 cgroups, one in resource A and one in resource B. We can't infer that they're related because they don't necessarily have to contain the same processes. With a single hierarchy, we can now make these kind of decisions which span multiple resources, and things which were previously not able to be accounted for now can be accounted. We'll go into that more in a moment. We also have granularity at the thread group ID, not the thread ID level. This is kind of a contentious change, but without extensive cooperation, thread granularity for cgroups doesn't make a whole lot of sense. Programs need to expose their intentions somehow. Threads need to expose their intentions somehow. And there's no real standardized way to do this in Linux. Like you can set the COM of your process and like say it has the name X, so it should be in this cgroup or something like that. But it's really usually very, very difficult to reason about how it should act in a lot of cases. One of the reasons it's really difficult to reason about in v2 is now that we have this unified hierarchy, many resource controls simply don't make sense like that. Like in v1, you could have separate threads from the same process in different memory cgroups. How are they supposed to compete for memory when they share like shit tons of memory? It doesn't make any sense. Yeah, so this is kind of an attempt to make things way more simple. Like there's a real focus on simplicity and clarity in version 2. And in many places in version 1, designs simply follow the implementation. We didn't know exactly what was needed, so it was made as flexible as possible, and it came to kind of bite us in the arse. The idea here is we should provide a framework that guides towards a correct solution instead of requiring people to understand all of the pitfalls, which is like a recipe for disaster. Another new feature in version 2 is this addition of the no internal process constraint. So this means that cgroups with processes cannot create child cgroups if they have those processes and they have controllers enabled. Say you have the CPU controller enabled in some part of the hierarchy. To put it in another way, the cgroups in red here either have to have no processes in or they have to have no controllers enabled. This is for a number of reasons. So generally, child processes should not compete for resources with their parent. That usually doesn't make a whole lot of sense. And implementing reasonable resource competition between children and parents is really, really hard, actually. It's like a pretty difficult technical barrier. One reason is because you now have 2 different distinct types of objects competing against each other. So say I have, I don't know exactly how Kubernetes works, but I guess it has an agent. So say there's an agent for Kubernetes in I, and it launches some tasks which are in cgroup J. So now we have to decide how we should share resources between the processes in I and J. So we have a C group, J, competing against a separate object, which is a process or a set of processes in I. There are a whole bunch of ways you can reason about how to solve this problem, like maybe each process in I is a separate implicit C group in itself, or maybe there's kind of like an I prime C group, which is all of the processes in I. But ultimately, we shouldn't be making this decision for you. You should be making this decision. That's why we leave it up to you to decide how you're going to distribute resources amongst the hierarchy. The root C group is kind of a special case for resource distribution. Each controller needs to decide how it's going to handle the root C group and how it's going to handle resource distribution to root C group processes compared to the leaves. So obviously breaking the API is kind of a big deal, right? This is like a very, very major kernel API. I already just gone over how many things use it. So we need a good reason to want to break this. So version 1 generally works acceptably in pretty basic situations, but it kind of gets exponentially complicated with complex use. And as I mentioned in version 1 design, often followed implementation. So reworking kernel APIs after the fact is really difficult, and we'll go into some practical examples of that as well. Even for stuff which was designed pretty well up front, use cases for cgroups were not really well fleshed out yet in the years leading up to 2008. It was kind of hard to guess at the time how containers would be used or what it would look like in 2017, right? This led to a whole bunch of overflexibility in all the places you don't want it, a whole bunch of complexity in all the places you don't want it, and yeah, to fix these fundamental issues, we need to have a new API break. So I've gone a lot over the theoretical. It's very important to understand that, to understand all the things we've been doing this for. So I want to go over why we're doing this. Not only what we're doing, but why we're doing this. So, OK, it's Q&A time. When you write to a file in Linux, what happens? I've had the word inode said. That's anyone else wants to say something about? Sorry? Page cache. Exactly the correct answer. So you don't really write to the disk. You make a write syscall, and that, from your application's perspective, once we've written a dirty page to the page cache, it can go on pretending about its merry way that it has been written to the disk. But of course, it's not been written to the disk because that would be extremely non-performant. Typically, it gets written as a dirty page to the page cache, and then some indefinite time later, based on the dirty page ratio or the number of seconds we allow for expiration, a kernel worker, pdflush, comes and says, I am going to now flush all of, or some of, the dirty pages to disk. And that operation happens distinctly from the write syscall which you issued inside your process. In version 1, we can't account for this. This is a non-trivial amount of disk for a significant number of applications. Like, we spend a lot of time writing stuff, and then it gets flushed out to disk. And then we don't understand where this page came from that we're writing to disk. The reason it's difficult in version 1 is because we have separate hierarchies per resource, and writing the page cache is a memory operation, and writing to the disk is an I/O operation. And between those points, we've not managed to track where this originally came from. In version 2, we can actually track these. In version 1, these went straight to the root C group, where I told you can get accounting, but that's about it. You can't do any limiting, for example, or any kind of resource competition. So now we're actually able to count these towards your C group's limits and take appropriate actions. For example, we can understand the relationship between I/O and memory use for a write-back. We can not only hold back some kinds of allocations if they're too costly, but we can also perform kind of reasonable actions based on I/O or memory pressure on a C group in general. So V2 is also generally kind of better integrated with subsystems. Most of the actions that we could take in version 1 based on thresholds, say a memory limit, were generally kind of crude or violent. For example, killing a process when you reach a memory limit is pretty violent. Like, most applications don't react very well to being kill-9'd. That's generally holds true for most kinds of applications. And yeah, you had basically that option, or you had another option, which was to set, I want a user space handler, and that user space handler will do a thing called freezing your process. Freezer is a feature of cgroup v1 where instead of killing a process, you can write something which freezes your process in the current state it's in. Then you have some worker which comes along and decides based on some context which it has about your whole system, I am going to raise the limit, or I'm going to kill those processes, or I'm going to get a stack trace and kill them, or whatever it wants to do. Basically, we allow you to freeze it and come back to it later. But this is really doesn't work very well in version 1. In version 1, the place we stop is not well defined at all. Like, it's entirely possible you will stop in some kernel stack which we don't know how to get out of. Like, we end up in like some place which is we're not able to restart execution. This also meant that when you attach GDB to get, say, a stack trace, which is a really common operation for some frozen process, I want to see what it was doing when we froze it, your GDB would often end up in uninterruptible sleep, which was pretty bad. Not usually what anyone wants when debugging, unless you are looking for really long-term job security. So we also have like some kind of soft limits here. We have one called soft limit in bytes in V1. I literally don't know anyone who understands how soft limit in bytes works. I have read the code and I still don't understand how soft limit in bytes works. So in V1, there is a soft limit, but it has like all sorts of heuristics based on global memory pressure and local memory pressure and cgroup memory pressure, and it's really hard to infer what it's going to do in any given moment. Like generally, I think it's not something which anyone can reason about how it should work. So for the purposes of my talk, I'll just pretend it doesn't exist. So now in cgroupv2, we actually have these, and we tend to have clear thresholds on hard limitable resources. For example, we have files with min, low, high, and max, where min and max are absolute limits, like a memory limit where we kill you. And low and max are best effort. I'll go more into how, low and high are best effort. I'll go more into how memory.high works in a moment through reclaim. Like I said, memory.high works based on reclaim, and essentially the idea here is that you would, instead of killing a process immediately, try and reclaim some of the memory. The idea is that we're trying to infer that we want to try and dial back the uses of the application. We want to try and throttle the application. We want to try and reclaim memory for the application instead of just running straight up to the killer, which is kind of a more crude action. This also means we can deal with temporary spikes in usage way easier. Say your memory usage goes like this. In V1, it's quite possible when you reach the peak, you're going to get killed and that's the end. But in V2, we can actually try and like slow you down a bit and reclaim some pages and then come back and go on with our merry life, which is generally kind of better. The notification API is also kind of dramatically improved in V2. It's a way to tell someone when a cgroup has changed state. So it could be that we have no more processes in the cgroup. It could be that something in the cgroup. The idea is something changed and we want to know about it. Systemd, for example, uses this to track processes which are changing state or which are exiting or starting or whatever. In version 1, this exists, but it can get really expensive. So to get a release notification, which is the notification we get when there are no more processes in a cgroup, which might mean say your daemon has died, you have to specify a release agent ahead of time. This is literally you give it a path to something on your system which it should execute every single time that we run out of processes. The problem is, for some kinds of use cases, you might be expiring a lot of times a second. And we have to now clone, say, 1,000 times a second for your 1,000 release events, which is not really what you want. So there is also for other events, like, say, something we have event-fd or poll support. But it kind of makes sense, since these are all files, to have more file-based APIs, like inotify. So in V2, we have inotify support. You get a modification event when things change. And yeah, all events now support event-fd with poll. And generally, this is like an easier API. User space utilities already exist. You don't have to write your own. You can use like a notify wait to get notification about cgroups. You don't have to sit around and write your own stuff. And the idea here is you have one process which can monitor your entire cgroup hierarchy instead of having an ON representation of clones for every single event which is fired. So utility controllers are controllers that don't manage a resource directly. Essentially, what a utility controller is it's a hierarchy which is for a user space utility, and that utility takes some kind of actions based on its hierarchy. For example, in V1, I don't know if people are familiar with a tool called perf, which does tracing. Essentially, you can tell perf, I want to have a particular cgroup and monitor the process in a particular cgroup, and it will get all sorts of counters and expose them through the hierarchy. It does this through its own controller called perf event. The same goes for freezer. When you want to freeze a process, you would have to put it in the freezer hierarchy and do some particular things, like write to a file, I want this to be frozen, or I want this to be unfrozen. But to do this, typically what you actually want to do is get some other hierarchy and then clone it and then do stuff to that hierarchy, which is how a lot of people implemented their stuff, and it results in like a whole bunch of race conditions and horrible outcomes because you end up like trying to replicate, you're trying to imitate a unified hierarchy when there isn't one in version 1. So the unified hierarchy is also kind of a response to how people use C groups in general. Since in v2 we have a unified hierarchy, like it's pretty difficult to screw this up. Touch wood. So in version 1, there's like also a whole bunch of inconsistency between controllers. There's two typical forms for that. One is inconsistent APIs for controllers which do almost the same thing. For example, we have I/O and CPU, both of which are weight or shares based, but they have completely unrelated APIs. You have to learn two APIs and all of the pitfalls of that API, then go and learn the other API as well, which is not really an ideal way of going about your life. Again, great for job security though. But yeah, in version 2, we've kind of made a concerted effort to make the APIs which should be similar. And this has been kind of an intentional goal, but it's also something which is just inherent to having a unified hierarchy. The other problem is inconsistent C group semantics. So in v1, most C groups inherited their parent's limit, but some do not. Some treat the C group hierarchy as if it was just nothing, and they don't care about hierarchy. They just give everybody everything or whatever they ask for. So it kind of makes sense to have a single way of operating. So in v2 also, the unified hierarchy kind of enforces that you do this in a correct way, and also in a unified way. v1's over-flexibility also contributed to like a number of API problems. Not only are some things difficult to do in v1, some of them like this are actually impossible to do, which is kind of bad. So for example, in v1 we had memory.limit in bytes, which was created towards the beginning of C groups when memcg was created, and it was supposed to be the memory limit in bytes, as you'd expect. And then somebody said, oh, how do I limit kernel memory? And then we went down this path of, oh, how do I limit TCP buffer memory? And then because you can't refactor kernel APIs after they're already in the kernel, you ended up with memory.limit in bytes, memory.kmem.limit in bytes, memory.kmem.tcp.limit in bytes, memory.kmem. Blah, 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 and memory.swap, and all sorts of things. You ended up with a single limit per every single type. The problem now is, say we are that person who wanted to set a limit on TCP buffers. We ended up with a solution which looks correct and doesn't work at all. So we set a limit, say with memory.kmem.tcp.limit in bytes. Then we set a general limit for all the general types of memory with memory.limit in bytes. And now, even if we have gigabytes and gigabytes of pages free for us to go and write, if you set a limit on the TCP buffers and you go one over, we just kill you. It's the end. Which is not really how anyone wants their application to work. And unfortunately, this API has caused numerous fatalities to processes as far, at least inside Facebook, which has been kind of amusing and terrifying. So yeah, so like again, having a unified limit generally kind of makes sense. So yeah, we have these new unified limits, memory.high and memory.max, which operate on basically all kinds of memory. From practical use, merging these into one memory limit seems to work best and be what most people want. This means you don't get those nasty surprises like getting killed just because you allocated like one TCP buffer to memory, which seems kind of harsh. And if you really need separate limits for one particular kind of memory, the proper way to do this is to create a new controller for that type of memory. For example, it was widely thought for a while that we could limit the number of PIDs in a C group by limiting certain kinds of kernel memory. But that turns out to be really, really hard, actually. It's like not something which is easy to do. So then the PID controller was created to provide that interface. It actually, agnostic of memory, provides an interface to limit PIDs. And the same if you want to limit TCP buffers or whatever, you just have to create a controller and use that. So if you go to facebook.com now, there is a 1 in 10 chance that you will hit a cgroup2 server. We easily run the largest cgroup2 distribution in the entire world. It's in the tens of thousands of machines, and we're really heavily invested in cgroup2 for a number of reasons. And one of them, of course, is like limiting the failure domains, like I mentioned at the beginning, and getting a better handle on your system services, but also being able to manage kind of resource allocations at scale. Say you have a data center and you want to run it in an efficient way. It can also be a big win for that, and it's something which we're looking into. We run, as you may have guessed from my previous mention, we run cgroup2 managed with systemd, and one of my teammates, David Akavalka, gave a talk at systemd.conf last year called deploying systemd at scale, which goes over kind of how we use it and how kind of gives a kind of a sister talk to this one. So we're a huge contributor to the core of cgroup2. We have 2 of the core maintainers at Facebook, and we're continuing to drive innovation here. So cgroup2 has been stable for a little while now. That doesn't mean that there isn't still work to be done. I've already been saying like some of this is for future changes. The core APIs here are stable, but there definitely is a whole bunch of functionality we're still working on. So when thinking about cgroups and what people want to limit, most people think of 3 kinds of things: I/O, memory, and CPU. We have 2 out of 3 currently in the Linux kernel. The CPU controller is super important, but it's not yet merged into the mainline kernel. The CPU subsystem folks have a number of reservations about the way that the CPU controller and cgroup2 in general works. They have some concerns about the process granularity versus thread granularity and like the no internal process constraint. We're in like a dialogue with them about how to move forward, and we are getting there. But yeah, there are some compromises being made here, and hopefully it should be merged soon. There may also end up being a syscall interface for some kinds of thread control, but we'll have to see how that goes. This is kind of like a bonus as a general kind of Linux. It's something that we're working on alongside cgroups, but will hopefully benefit Linux users in general. One thing we've never had in Linux, or pretty much ever in Unix, is a good measure of memory pressure. We have some kind of related metrics like free memory, or free memory without cache and buffers, or whatever, or if you're slightly more up the sysadmin ladder, you'll say like, go look at page scans or something like that. But even with all these metrics, it's really hard to tell pressure from good usage. It's really difficult to determine what is actual bad usage. So one proposed measure we're working on is to track page refaulting. So the idea is every time you fault in a page of memory, we will record it, and we will find pages which are repeatedly faulted back and again. So the way this works, to understand how this works, you kind of have to understand how memory management in Linux generally works, how the working set works. So when you fault in a page, it goes to the head of this inactive list. The inactive list is a list which the kernel considers to be pages which may not be in use by any application anymore. When you reaccess that page, say you access it again, we promote it to the head of the active list. The active list is pages which the kernel considers are probably in use by some particular process. As you repeatedly fault pages, they push pages further and further down towards the end of the inactive list. When we do a reclaim, the reclaim comes from the tail of the inactive list towards the front. This means we're more likely to reclaim and free pages which are considered to be inactive for the longest time. Usually this works pretty well. But what if we see pages which are repeatedly being faulted back in? Well, what this probably means is we have pages which are repeatedly being reclaimed and then are going to become non-resident and then are being faulted straight back in. Ultimately, what this means is we have too many pages which we consider to be frequently used. We have so many that they can't fit and they keep on getting pushed out. And this is kind of another way of saying that we've exceeded our memory limits for the system. And we're thrashing as a result. And this is one place that we're really working on using as a potential metric for memory pressure. So we also now have tracking of non-immediate events like page cache writebacks. Currently, we have this working for I/O memory resources, but one thing we don't have is CPU cycle accounting for that. If you're doing a lot of page cache writebacks, it's entirely possible that we can account for your I/O and memory use now, but we can't account for the CPU cycles we spent doing it. That's something which is coming and hopefully will be done pretty soon. This also goes for stuff like packets coming in on the network card, which we don't yet know who they're going to. We can then retroactively say, hey, this was part of your cgroup allocation. The I/O controller is also currently merged, but not work conserving. What this means is we don't redistribute idle resources to other cgroups. This is a fairly important action item because otherwise if you set some limit, then the way it ends up working is you set an absolute limit and it can never go above that amount of I/O, which is not typically what you want. And that's something we're working on. V2 also has a whole bunch of improvements on what kinds of I/O we can account for. For example, now we can account for writeback. But one lacking aspect is tracking of file system metadata, like dentries and INO metadata. File system metadata is generally pretty hard to account for in the kernel. But this is something we are interested in working on, but it may take some time. I also just talked about this refault metric detection. And another interesting point is freezer, which I've just been talking about having some problems with in V1. I mentioned it has some kind of situation where you'll freeze something and then you can't even get a stack trace because your process goes into an interruptible sleep. We're making one which kind of has semantics which are way more similar to sigstop. So sigstop is very similar to what people tend to want, and it stops in a very well-defined part it stops in a very well-defined stack. Like, in general, it makes a whole lot more sense to use that kind of mechanism to do this. This should also avoid like processes going into D state when you attach. So I talked a lot about selling you on cgroupv2, so hopefully you're interested in trying it out. So here's what you need to get started with version 2. First, you need a kernel above 4.5. If you don't have 4.5, we do actually have experimental support for a very long time in the Linux kernel, but we don't have a stable API before then. So here be dragons, basically. You will be in a world of pain, probably, if you try and use it before 4.5. You can do it with the developer flag, which I won't mention, because I'm sure everyone will go do it afterwards. So once you've got kernel 4.5, there are more or less two things to do here. Turn off the V1 controllers, and turn on the V2 controls, which happens implicitly when you disable the V1 controllers. So you pass this flag, cgroup no v1 equals all. This tells the kernel to disable the v1 controllers. Essentially, it tells it to release control of those controllers for use by other cgroup hierarchies, i.e. cgroup v2. It doesn't make sense for like a resource to be controlled both by v1 and v2. In theory, you can have mixed mode where some resources are controlled by v1 and v2, but again, there be dragons. Like, nobody really knows how this is supposed to work. The second thing is to tell your init system that it should mount and use the new cgroup v2 hierarchy. With systemd above v2 to 6, you can do this with this flag to mount the unified cgroup hierarchy. This tells systemd not only to mount the new hierarchy, but also to change its behavior to use the new hierarchy properly. Typically, having your init system mount and do all this for you is the best way. You can manually mount the cgroup 2 hierarchy with that, but yeah, like that's probably not going to work very well, because if you don't have the cgroup hierarchy managed by your init system, I don't know how you expect to have a reasonable system, to be honest. So if you're interested in hearing more about control groups, please do come and talk to me. I'm happy to go over anything that I've been going over and anything to do with v1 or v2. Happy to go over any questions that you have about cgroups in general. And yeah, if you've used v1 in the past, which you almost certainly have, and you found it difficult to use or reason about, please do come up to me and let us know what you think. Thanks.